Indeed, good morning. So I will talk about a very specific case of QED radiative corrections for reasons that I will outline in a moment. I just want to have here on the first slide disclaimer that part of the material is taken from my PhD student in Munich, Dominik Steffen, who is working on the analysis of this very channel and has very nicely proceeded in this regard. One of the issues that is still under construction, under work, is radiative corrections, in fact, and I hope I can display how and why and how we want to do that. In fact, it would be good to go to the next slide. Here we go. Okay, so I will give a short intro into the physics case of why we want to measure pion-photon collision into pion and pi zero. And then we'll show the corrections, the QED corrections. They have been calculated some 20 years ago. So in principle, that is known stuff. But well, we always prepared for some surprises there, of course. And well, not too many, but there are. And then we have a look at the application to the experiment in data analysis, how it interferes with backgrounds that we have, and how normalization is done. And then to the real internal corrections, the Bremsstrahlung corrections. That is maybe the case why I thought it's worthwhile to bring the case here, because this is a comparatively simple case of QED radiative corrections. There's only one charged arm, right? So the photon and the pi zero obviously do not radiate. And yeah, you don't have this issue with the tracing, that if you try to trace some of the results that theoreticians tell you, then it usually, if we consider the electron-proton case in this huge variation of the gamma matrices, and then you just have to believe what comes out. Here the formal stuff remains more compact, and I think it's a nice showcase. Although it's not up to me to show the formula, just to also give this disclaimer at this point. And okay, so this as my plan. I wanted to make another remark. Well, any case, let's go to the first part, to the theory motivation. So we know that the QCD Lagrangian features at the chiral limit. So for massless quarks, the approximate flavor symmetries, so left and right-handed fields decouple. And in principle, if this would be the full story, then it would translate directly to parity doublets in the mass spectrum, but this is of course not the case. We have the 0- quantum numbers being almost massless, and the corresponding 0+ only at quite high energies. And good question then why the chiral symmetry is not manifested in the spectrum, despite the isospin symmetry, which means that at least the lowest quarks, the up and down quarks, are both light and of similar mass at least. and the corresponding eightfold way. And well, the answer is the Nambo-Goldstone mechanism for spontaneous symmetry breaking, which features 8 massless and spinless Goldstone bosons. So at SU3, including strangeness, it's the pions, the kaons, and the eta. And then this symmetry, they are not massless, of course, is explicit broken by the quark masses. And in addition, the symmetry breaks down to its vectorial, so the symmetric part between left and right-handed and not anti-symmetric. And so that's why it's 8 Goldstone bosons and not 9. And well, the symmetry can still be exploited then as an effective theory with a power counting scheme, and gives predictions of low energy QCD, which in fact reach quite far. So in principle, this QCD Lagrangian in chiral limit again features the axial, so the antisymmetric left and right-handed symmetry, but this 9th unnatural light meson is missing. And so this is anomalous symmetry breaking, that the symmetry of the Lagrangian is not there at the quantum level, and so it does not lead to conserved neutral currents, and the eta prime is normally heavy, let's say, for hadron. Now, how do we implement that then in ChiPT? That the chiral anomaly is taken into account by Wessumino-Witten terms. So you contract your vectors that you have either with the fully antisymmetric Levi-Civita, or you can contract if you have 3 momenta and a photon by the polarization vector of the photon. And this describes then the coupling of an odd number of Goldstone bosons. So if the pi0 in terms of strong interacting system just disappears when it converts into 2 photons, or if the photon couples to 3 pions. And then there's a whole group of linked couplings to it, which all boil down to a single free parameter in the whole system. So we determine typically what is better measured best is the charged pion decay constant, f pi. And from that, then the others can be calculated. For instance, the pi0 decay has then this form where the number of colors explicitly appears, as well as the photon to 3 pion coupling, where the pion decay constant enters in the denominator to the 3rd power. And you see here that the prediction from theory is claimed to be really precise on the percent level, sub-percent level. It's believed that this is a firm prediction. Now, how to measure this photon to 3 pions coupling? As one of the most definite tests of this approach to low energy QCD, it is accessible via the reaction pion photon scattering into 2 pions. This has obviously as a low energy coupling exactly this term. The trouble is that we don't have pion targets at rest, as we know, so we cannot use a real photon beam colliding with this kind of target. And the way out are Primakov reactions, where you scatter the pion off in the nuclear fringe field, which is purely electromagnetic at some distance at least. And there you approximate this scattering as scattering of quasi-real photons. And so this process that we have sketched here before is embedded into the Primakov reaction. And the kinematics of this embedded process is very simple. It's a two-body elastic or two-to-two body process, which features then in the center of momentum only the one scattering angle. And in principle, there is a spin of the photon involved. This is the only quantity that one may have to sum over, or which could lead to some observables. But the outgoing pions, of course, and the incoming pion are spinless. So how does this cross-section look like for the embedded process? Pion photon goes to pi minus pi 0. It is depicted here. The formula basically it is proportional to this constant f3 pi, and then it has kinematic factors which add to it, and this alone leads to the red curve here. And then, of course, in this process at higher energies, pion and photon can couple to the rho resonance. This, in fact, fully saturates then the cross-section at some point. And the rho has this, or this is what I meant by this, the rho decays, the rho minus in this case, to almost 100% into pi minus pi 0. And here's the relative factor given as a gray line, which modifies this non-resonant part of the cross-section. And here you see the full prediction then in linear scale on the cross-section level. And here you see the non-resonant part, and then how the interference with the rho enters. And you see that the Breit-Wigner shape of the rho is quite modified in interference with this non-resonant part at higher energies than destructively. And so we will distinguish this low energy part and the rho region part in the following. This low energy part, it goes, let's say, up to 3 or 4 pion masses. The rho resonance is at 5.5 pion masses. And this low energy region was first attacked by an experiment at Serpukhov, published here in this paper. They had only few events, and what means few? So few hundred, but still not a huge statistics. And it went up to, so this goes up at 16, you would have 4 pion masses. There the spectrum is already cut out by the acceptance. This is also a Primakov reaction, and at lower energies, your spectrum gets cut. We understand this a little later. And you see the most of the events are here at about 3 pion masses. And here at threshold, you simply don't have statistics in this experiment. And okay, from this experiment, the constant was then extracted by just taking out the terms from embedding the cross section and taking out the kinematic terms, as you see here. And the result is given here. It's almost 13 GeV to the -3. So this is in a strong tension, even with the large error bars that they had with the expectation from KPT. And that was for a while a good question, how could that be? Because this effect on the order of 20%, almost 30% is not easy to understand, even if one says the radiative corrections at this point have not been applied. But there was surprise when this was then closer investigated. The so-called Ametya paper from 2001, together with Knecht and Talavera, they have investigated the radiative corrections for this process. So photon loops on the one hand, and then of course the real corrections with photon radiation from the charged arm on the other hand. But they pointed to the fact that there's also an additional graph in the business, which they depict here. So they calculate in general the pion to the photon to 3 pion coupling in general. So the photon is always on one side and all the pions on the other side. And of course, for our process, we have to flip over or one of the charged pions. And so I translate this here in the experimenter's view. So you have a pion and a photon colliding. So you have to flip over one of these arms. And then you have a photon in the exchange. And this photon can merge with the incoming photon via the coupling of the pi0 to 2 photons, which is of course known by its decay. It can form the pi0. And that's in fact the most dominant part of the story. So they point to this T-channel 1 photon exchange contribution in the process. But then this is comparatively simple to calculate, but you have to go through all the math of the loops to prove that that is the dominant part. So formally, you have this point coupling F3 pi and the kinematic factor, and then this T-channel exchange has the typical form with the T-pole. So it's dominated by 1 over T with some constants. And yes, so we have recapitulated this whole paper, and in fact it was, again, I don't know why that is, but it's always possible to compactify drastically the expressions which are given and to simplify them, and then in the course you discover like factors of 2 and so on, which don't play a big role in the end, but it is something where me as an experimenter, I'm lost, right? Because if I'm pointed to the paper and they say, well, someone calculated that already, and it's written in a really ununderstandable way, I don't know, maybe you disagree on that, but this paper is really, really tough. And then even the formula you cannot take as they are. That's really a burden in the business. And yes, please.
Which numbers was used in just experiments, and how which are Coulomb corrections?
Yeah, for the Serpukhov experiment, they took 3 targets. They took carbon, a lead target, and some copper target, and they show in their paper that you have indeed the z-squared scaling of the process. At this stage, for lead especially, you do expect large, like 30% Coulomb corrections, but for carbon especially, it is a small effect. And well, we chose for the compass experiment a nickel target. Yeah, copper or nickel, that doesn't give each other much. Where you have to keep this in mind, that there is a Coulomb correction, but well, how does it factorize? Probably it doesn't factorize even. It would be nasty to implement it in a correct way. But maybe we come to this later. At the moment, we are in the embedded process, right? And so we don't have Coulomb corrections at this stage. It only comes with the Primakov. Okay. So as I said, this part here is the dominant one. And this is how the correction looks like if you draw it with respect to the CM energy that you have here. It amounts to some 33% of correction to the basic cross section. And then it's the integral over all angles is the red line, and then there's quite a strong effect. Yeah, it goes with T, so that's the cosine of the scattering angle is involved, and of course you get here this collinear divergence. Can I call it divergence? Well, it gets larger and larger if you go to forward angles with your pion, then the correction is really big, and only because of the phase space, which closes then. So the most dominant part comes from 90-degree scattering. Yeah, it's a one minus cosine squared, something like this is the kinematic factor here. And this gives then dominance here to the second line, which is when the cosine is 0. So for backward angles, you have a smaller correction. For forward angles, you get a larger correction, and this averages out here. We need to understand it on this level, of course, because in our experiment, we do make cuts on the kinematics, and we are sensitive more to backward angles. So we cannot take simply the overall correction, but we have to take into account somehow our theta coverage. Now, the other corrections where my complaints apply in terms of the correctness of the terms, correcting as much as Norbert Kaiser, who helped us with that, claims to have it correct now. So we simply believe they're on the next stage, is given here. So there's several terms contributing. We don't go too much into detail here. I just want to display that because we have again the effect of a theta dependence, and this color shading should reflect that from the different terms which appear. The light shaded ones are the ones where we do not have acceptance, and then the stronger ones is what we need. And there is some cancellations between the terms, and in the very end, you see here converted to the relative effect on the cross section. And there's only small numbers. I give on the next slide an overview plot where you can better read the numbers. The important message here is that the rest of the corrections are on the 0.5% level. And so doing them more or less correct doesn't play really much of a role. You demonstrate here that you have this 30% correction from the photon exchange diagram, and the rest is really small. In principle, you should apply, of course, these corrections, but they don't change really the result. And applying these corrections, of course, is an issue because they depend on the kinematics. And so a fudge factor in the very end, when you have some spectrum of S or so, and you say, this is my radiative correction, you cannot directly give this as a factor, but the cleanest way is to apply it on the event by event base to calculate it for each kinematics that you have, and then look at the overall effect. Yeah, this is the cleanest way, and at least for the virtual corrections, this is how it works. So here you see a compilation of these results. The black line is again the photon exchange. It's marked here with 1 gamma correction, which then goes up to these 32%. So this is out of scale here. And for this one may include the pion shape or the pion size effects in chiral or VDM approach. And then you get some modification of that, which in fact is more relevant than what I've shown about the photon loops. Yeah, you see here that this is an effect which stays around 0.5%, and it's weakly dependent on the square root of S. And then you have 2 contributions from real photon emission that we come to later. And there is a so-called CM contribution, which is formally the more challenging one, which is the term which is independent of the photon energy, and the so-called universal factor, which in soft photon approximation is independent of the frame in which you evaluate it. And here this green line refers to a cutoff of the soft photons at 10 MeV. Yeah, this is already quite large. One has to realize at let's say 3 pion masses, we are at 700 or how much, 500 MeV rather. And then 10 MeV is relatively already sizable. Okay, so taking into account this photon exchange graph, calmed somehow the physics case of the chiral anomaly. So I remind here, this is the original result, and then applying all the corrections that Ermittler and colleagues discuss, brings down the value to 10.7. And you see here, if you take into account the comparatively large error in 10% level, that one is quite well in agreement with the theoretical application, theoretical expectation. But of course, this asks for more precise data to make an additional point here. The other point which comes into the game if we measure at high energies, and then the S spectrum or the 2-pion mass spectrum gets enlarged, is the row resonance. So as mentioned before, the process can also proceed via forming the row resonance if the CM energy is sufficiently large. And then you get this shape as shown before, and measuring this, the size of that, of course, is a measurement of the rho to pi gamma, the radiative width of the row. And exactly this process has been used by Capraro and colleagues, also a measurement at the CERN SPS, very similar to what the COMPASS experiment is doing, measuring on copper. And they have comparatively nice statistics in the row region, or what means nice, I mean, it's sufficient to get the radiative width of the row with a precision of 5 to 7%. And it doesn't cover the threshold region. This is where the Serpukhov data sit. Still, this is quite limited in statistics, and with the COMPASS data, just to give a number, we have about a factor of 100 more data there. So here we should be able to give quite a precise value on the row radiative width if we get all the systematics under control. And then, I mentioned this also before, that this interference of the chiral anomaly and the row leads to a specific damping of the row resonance at higher values, where it goes to a minimum, and then later on also the row 3 is comes into reach. A few words on this experiment. So COMPASS has attacked this already quite some time ago. We took this data in 2009 with an 190 GeV hadron beam, which features the majority, 97% about of pi minus, and those are identified in Cherenkov detectors upstream of the target, which is a nickel disk of 25% radiation length. And then in the spectrometer, the pi minus is measured with high precision, its momentum and direction, and the produced photon in a colorimeter with about 30 micro rad angular resolution. And this allows to select events at very low Q square. And one of the real challenges of this experiment then to get the Chiral anomaly is to get the luminosity correct, because it's a cross-section height that we want to measure. And so because the luminosity is not that precisely measured in the setup, we make a relative measurement compared to the free kaon decays, whose lifetime is measured very precisely. And so by investigating the decay of the kaon component in the beam, which is very well known, into 2 or 3 pions, we get a good measure on the luminosity. So the full plan of the analysis, as my PhD student has depicted it, you have the pi minus pi 0 events on the one hand, and you have the respective Monte Carlo for it, which gives you the acceptance. And then we have these 2 big steps in between interpreting these spectra. And the first is the background subtraction, and the by far biggest background, which also covers, unfortunately, the radiative tail, is events from pi minus pi 0, pi 0. So this channel has to be investigated quite in detail with it. It makes a problem because it is not possible only via the Primakov reaction, which also goes to this final state, but this is possible also by strong interaction, because you have 1 pion going to 3 pions, and then at this very high collision energies, you get this final state via Pomeron exchange. And so in forward directions, you see many of those events. And we have a partial wave analysis for this. Of course, this channel is interesting by itself. So understanding all the resonances which contribute. For us, this is a very nice background estimator. And then we have to analyze all the different kaon decays and use this to normalize the luminosity. And this finally allows then for the extraction of F3 pi. Once more to this Primakov reactions, if you're not really familiar with it. So this is the basic idea is to use heavy nuclei as a photon target. And useful number to keep in mind the electric field at a few nuclear radii away, where you don't have strong interactions anymore, is 300 kilovolts over 1 femtometer. So you have quite a strong field there to rip the pion apart in some sense. And this, of course, works then only at large impact parameters or at ultra peripheral scattering. This is seen in terms of very low momentum transfers. And here is shown the spectrum of that and the respective formula. So this is the Weizsäcker-Williams factorization into a flux of quasi-real photons entering the form factor and the respective photon propagator. At this stage, one has to consider the Coulomb corrections, how this term is modified. It had been calculated for our kind of Primakov reactions by Feld and Tengblad from Uppsala. And we take this part into account. And one has to keep in mind here, sometimes it's said that you don't measure really with real photons, but the virtuality of these photons in the peak is on the range of 10 to the minus 5 GeV squared. Yeah, so here on Q itself, it is at 1.5 MeV, but then so I insist on, and I like to present the spectra in linear in Q, because then the spectrum is less spiked. If you square that, the small values get even smaller, and the tail gets longer, and you just see one spike and nothing more. Here you see a spectrum, and in any case, you have a peak then at 1.5 MeV, or a little larger. This is the minimum value for Q, and then you have the maximum close after that. Yes, you had a question.
I was waiting when you would come to hadronic contribution to the framework. I don't see that. I am wrong.
Yes, so the hadronic contribution to the channel itself, so to pi minus pi 0, doesn't work. Yeah, so well, at least at high energies, when pion exchange and all has died out as compared to the Pomeron exchange. So this is really negligible. How it enters is the just mentioned 3 pion final state. And this we have to put in the simulation. And we know, because we analyzed them at the same time as the other data. They had been recorded at the same time. And by this, you get a very good estimate for this background. But I will not present this whole analysis here, because I wanted to focus. I give a few of the parts of it, because I wanted to focus on the radiative corrections part of it. Yeah. So I just mentioned on the side that it's actually the main part of the work, as usual, to get hold of the backgrounds. So indeed, I wanted to mention exactly the same thing here with this pi minus pi 0 final state. And it's of course not the same final state, but what happens is here that we have one soft pi 0 in this channel, or the 2 photons get lost, or it's strongly asymmetric, that you lose 1 photon, and then it imitates one real photon, one single real photon final state as well. So what we do is to have a full simulation for the final state, including the pi 0, and then by the model, we extend it to the full kinematics, and then analyze these data, how they would look like if we ask only for the pi minus pi 0 final state, and there is an overlap on the, let's say, 10% level that we have to subtract. Yeah, and here the argument again that the other strong exchanges, they go with 1 over the beam energy, so they are suppressed at 190 GeV. What survives is the Pomeron exchange. All right, then a few things to this kaon decays. We have 4 of them, which we analyze. It's the kaon decay into 3 pions, into 2 pions. So this is the same final state as for the process of interest itself. And then the 2 semi-leptonic decays into muon and pi 0, or electron and pi 0. And well, the full calculus of getting then in the end the pion flux, this is what we are interested in, is that it enters, of course, in how many detected kaon decays we have, by taking into account how many kaons we have in the beam with respect to the number of pions. Then the respective branching ratio of the decay we are interested in, the probability of a kaon decay in our decay volume, and the acceptance for the kaon decays by the spectrometer. So this has to be taken into account by a simulation also. And from all kaon decays, we have 4, which we are sensitive to. This is due to the trigger of the events. We trigger for a signal, for significant signals in the electromagnetic calorimeter, yeah, where we have a pi0 at least, or a photon. And so we are not sensitive to the pure leptonic decay into muon and neutrino, and also not to the fully charged 3-pion channel. But the others we can measure, and we can get a luminosity out of that. And I don't show results on that today, but this is under control. So all these results are consistent, and we get a good value for the luminosity this way. One issue which will bring us then closer to the real photon stuff is that for the kaon to electron and pi0 and electron neutrino decay, we want to identify electrons. And of course, you do this with the electromagnetic calorimeter. And there is some surprise. I was not too surprised, but Dominic and others, that the linear correlation that you see in the electromagnetic calorimeter and the momentum of the particle, it is a fine line. Yeah, it's nice. You see a correlation, but that's not all. You have quite many electrons which have high track momentum, so high energy in fact, but they leave a smaller energy in the cluster in the end of your calorimeter. And this is where we kind of lose the electrons. You see here the pions, for them it works nicely. If you make this cut, they don't lose as much energy as the electrons, but still they lose some energy in the electromagnetic calorimeter because their hadronic shower is started in these calorimeter blocks already. How does this come that there's electrons who escape kind of this correlation? This is due to material in the spectrometer, and we have a 2-stage spectrometer at Compass with so 2 magnets, and in between, of course, the particles make straight lines and cross quite a few detectors, and in them they emit Bremsstrahlung already, external Bremsstrahlung, and this predominantly goes into then 3 directions. So if you ask for the total energy in the calorimeter, then you find, in fact, the energy of the original electron. But what one does normally is to look at the cluster that is associated with the track and looks whether this energy matches the energy of the track. And well, we have some 20% of radiation length building up in our detectors. And so electrons can radiate quite a bit of their energy. And this you can see here, that simulation, but the real data look quite similar, except that we cannot simply distinguish electrons and pions as we can do in the simulation. And you see here the distance between the straight extrapolation to the cluster, so of this incoming beam to the calorimeter. And there we see quite some strong signal already. And then from the intermediate parts, we see a bow which now bends because the higher the momentum of the charged particle is, the less it is bent, and so the distance to the first point is smaller. That's why it's converging here. But you clearly see these three distinct lines, which in the end, that's one of the details, just to mention that, we have taken into account additional photons under these specific directions. I mean, you know the track that the electron took, and if it lost energy, you can reconstruct how this energy loss got forward, and by this we could enhance our electron sensitivity and reconcile at least to a good share the kaon decay intensity into this specific channel. For the pions, this does not happen. Pions do not do real external Bremsstrahlung, and so all you see is that the pion leaves at the impact point then a part of its energy. Okay, so now the radiative corrections must be implemented in our analysis scheme also somewhere. And the one thing we discussed already, that is at the analysis itself and putting it into a factor as an event-based factor to the real data, or as an overall factor to the obtained spectra. But well, this works for the internal corrections. For the internal Bremsstrahlung, so if in the process an additional real photon is emitted, then we have to worry what happens to these events and how do they overlap. And so here's shown the full phase space for this reaction now, that additional photon is emitted. And on the y-axis of this Dalitz plot, you have the photon energy. On the x-axis, it's the pi minus energy. And yes, one but last slide. Yeah. And you see here the most relevant point for us, where the photon energy is small. This is the transition, in fact, to the reaction without a photon. So you have here the original graph, pion and photon colliding to pi minus and pi zero. And then you take into account a small sphere of photons which go somewhere. And so the kinematics are calculated for a fixed scattering angle of the pi minus. And then its energy, it's a bit distorted by allowing for some real soft photons and the angles for the outgoing pi minus accordingly to get a valid kinematics. And well, this can be calculated directly. It's the tree diagrams for it. So emitting a photon from one of the two charged lines. And this one has to bring into coincidence with the overall factor that we calculate for the soft photon correction. And here you see now the events weighted with its cross-section. And of course, you see that the soft photons are by far dominant. Yeah, you see here on this scale, it's like 5 orders of magnitude more probable to have a soft photon than all the rest of the phase space. But this is kind of an arbitrary number, because the closer you go to this photon pole, the higher this cross-section becomes. And for implementing the radiative corrections, one has to define a handover point. We know this the cutoff energy, which one has to choose in the range here of about 1 MeV. Then the exact calculus of the cross-section and the approximation of this 1 over lambda, or this leading log term, as you call it, they are in coincidence with better than a per mil. So this doesn't have any effect. And then the photon energies, which are even lower than that, you take into account, you attribute to the correction of the elastic events. One issue here is that I always make this remark. It's maybe getting boring, but well, there's newcomers, so I allow myself this 1 over photon energy divergence has nothing to do with detector resolution. Yeah, there's it can be that you have a bad resolution detector. We heard about that, and then this doesn't play a role, this effect, but the 1 over lambda divergence is more severe. It is a real cross-section, and so having a factor which gets larger and larger, it applies in the end to a infinitely large cross-section, or at least to the point where the photon emission becomes more and more probable. And well, that's already the solution. I think, Jan, you pointed to that already, that this shape is simply wrong, because at this point, then if one photon emission is very probable, this implies by independent adding of the emission of more photons is equally probable. And then you have to take into account the higher orders. This is traditionally done by the so-called exponentiation that is inspired by the investigation of the cancellation of divergences by this famous paper of Friedrich and Zura, who have shown that for infinitely soft photons, the cancellations work perfectly, and that leads to exponential function in terms of how these terms contribute, which is equivalent to say that the emissions of these single photons are independent. But of course, this for any finite photon energy is not a valid statement, right? It's the same process, and the two photons are correlated to some extent. And I'm curious always to learn whether there's ways out of that, how to treat the double internal or several photon internal process, except for calculating really what the next order is. All right, and with this, I conclude. The idea to collect how to do radiative corrections on a more general level is, I think, a good one. But one has to keep in mind that every experiment, at least every precision experiment, requires its own radiative corrections to really worry about how do the formula look like, what are the relevant single photon processes and so on, and to put this in a connection with what your real apparative sensitivity is, what are your cuts and so on, and how does the radiative correction come into play here. And the most complete way is to take radiative events in the Monte Carlo simulation of your events, and then usually, at least this is what I never succeeded in the analyses that I did, that you fit your free parameters, be it proton radius or the pion lifetime, pion polarizability with it, or this chiral anomaly. You should normally then or in the best of all worlds, iterate the whole procedure to implement your adapted cross-section and demonstrate that this really then describes your data fully and not interpret any deviation. Okay, and of course, yes, transparency would be the best to achieve here. So to fully document how it was done and best with code that that survives time. And this, I think, is highly demanded because many have commented in this regard already that for old experiments, it's just guesswork what has been done, and that's then a bad status. Okay, and sorry I took more than my time, and thanks for your attention.